Hi everyone, thank you so much for joining us today. We have with us very special guest speaker, Khurram Javed. Khurram will be talking about real-time reinforcement learning using dynamic network. He is a PhD student at RLAI lab at University of Alberta and is advised by Professor Rich Sutton. He is interested in building algorithms for real-time continual learning for achieving goal in big world. Previously, he completed his M.Sc. with Professor Martha White on meta-learning representation for continual learning and worked at MILA with Professor Yoshua Bengio on Causality and TUKL-SEECS with Professor Faisal Shafait. He also represented Pakistan at 55th International Mathematical Olympiad and Asian Pacific Mathematical Olympiad, receiving honorable mention and bronze medal respectively. Thank you so much for taking out the time and really excited for the talk.
Thanks, Emma. Thank you for inviting me. So as I said, I'm a PhD student at University of Alberta, and I'm gonna talk about some of the research I've been doing over the past few years. Now, one component of this talk is going to be a live demo. Every time I've tried this live demo virtually, something has gone wrong, so something might go wrong today, but let's see how it goes. So my work is on real-time reinforcement learning. So I should first tell you what I mean by real-time reinforcement learning. There are two ways you can think of the real-time aspect of reinforcement learning. One is the idea that, well, your environment is real-time. Normally, when you do reinforcement learning, your environment waits for the agent to take a step. And the agent can take however long it wants to take a step, and the environment will just wait. Now, in a real-time environment, that would not be true. The environment would just keep going on. And if the agent takes too long to respond, it's going to lose out on performance. Now, if you think about a lot of real applications of reinforcement learning, this is true. If you're trying to do reinforcement learning, let's say on live audio data or video data, your sensors are going to keep sensing the word. They're not going to wait for the agent. And so there is this component of this paradigm where the agent is incentivized to make decisions quickly and in a short amount of time. The second way of looking at real-time reinforcement learning is that the agent should be able to learn in real time. So normally, if you think about reinforcement learning or deep reinforcement learning, what happens is that the agent interacts with the word, and then it stores the data, and then it does some learning with that data, but there's a delay between the time it receives the data and the time the agent updates its behavior. And this property happens in all RL algorithms. So if you look at value-based algorithm, for example, then normally what you would do is you would throw the data in a large replay buffer and then sample from that buffer, which means that you're not going to learn immediately from the data that you just saw. If you look at policy gradient method, something similar happens where you're constrained how much your policy can change from one step to the next. This is something that PPO does. And again, what as a result of this is that the agent does not learn immediately and in real time. So we don't want to do that. My goal is that the agent should be able to learn quickly, and we should be able to see learning happening as we interact with the agent. So let me more concretely define the agent environment interface before I go on. So there's an agent, there's an environment, there's an agent environment boundary. And in this case, the environment does not have any discrete time step, but the agent does. And this duration between t-1 to t, that's one time step, and this one is second time step. But because the environment is continuous, that means things can happen all the time. So for example, maybe some sound is generated at this point, and the agent receives it here. Similarly, maybe some light stimuli is generated, and the agent receives it here. Now, if the agent is going to receive it, then it's going to wait till time t, and that's when it's going to process it. And after processing it, it can make some decisions, right? So there's this environment agent interface. Environment is continuous. Agent is discrete. And the agent has a time step. Things can happen at all time in the environment, but the agent is going to buffer them, and then it's going to process them at time step t. And then it's going to take some time to make some decisions and send out some actions. Now, after picking the action, it has this small amount of time where any sort of learning or planning can happen. And in a real-time RL agent, all the learning that's going to happen is in this very short time step. So if this still doesn't make sense, that's okay, because I'm going to show you a demo of real-time learning, and I think then it'll make a lot more sense. So before I show you the demo, I have to give you one piece of background information, which is temporal predictions. These predictions are very common in reinforcement learning. A temporal prediction is basically you're trying to predict the discounted value, the discounted future value of a scalar. So let's say that you have some audio data stream, and it's going from left to right, and then you have a reward signal. And the reward is -1 here and +1 here. And your goal is to predict the discounted value of future reward. That's the temporal prediction. Then the prediction would look something like this, where the prediction starts going up before the reward occurs. And then as soon as the reward occurs, it goes back down. And then it's going to start going up before the reward happens. And then it's going to go down as soon as the reward happens. And that's because we're trying to predict the discounted future value of this cumulant, which means that you start predicting it before it happens. And if you superimpose everything, this is how it looks like. So let's try to see if we can learn a prediction like this. So this is the live demo part. Now what you see on the plot, this is the plot of a live audio of me. So as I speak, this graph moves. If I become quiet, it doesn't move. And we're gonna use this data stream to do some learning, do some very simple learning. Now I'm going to do one pre-processing that I'm going to transform this data into its frequency domain. So I'm going to apply Fourier transform, and we're going to get this frequency domain. So now you can see that as I speak, certain frequencies get activated. If I, for instance, whistle, you can see a much higher frequency getting activated. And the agent is going to try to learn something from this data stream. The third thing I haven't told you is, oops, this is, okay, is what's the reward? What are we going to try to predict? So this is the observation. What are we going to predict? So I have a clicker in my hand. You can see it on the slide. This is also a live video feed. And it has two buttons. If I press this button, that's a reward of +1. So you can see that as soon as I press it, in the plot below the feed, you can see the red line showing a +1. Press it again, reward of +1. If I press a different button, reward of -1. So this is our reward. That's our observation. And we're going to try to learn something. What are we going to learn from? Well, I have this keyboard. So I'm going to play a note, and then I'm going to give the agent reward. And let's see if the agent can learn to predict that reward in 10 to 15 samples. We want to see if it can learn quickly. Okay. So what I'm going to do is I'm going to play a note, and then I'm going to give a reward with this clicker that I just showed you. So let's play a random node. And reward of +1. So let's do this a few times. Let's do it 10 times. So now you can already see that the agent is predicting something. As soon as I play the sound, the prediction goes up on the prediction plot. So predict something, and then when I stop playing it, the prediction goes down. If I play a different note, I can give it a negative reward, and it can learn to predict something negative. So let's do that. Okay, so now if I play back the old note, it's going to predict something positive. I didn't even give it reward this time. If I play the second note, it's going to predict something negative. So learning is happening in front of us. That's what I mean by real-time learning. Okay, so how is this working? That's what I'm going to tell you about today. And let me show you something on the agent side now. What is exactly the agent doing as I make these sounds? So the agent, in our case, it's a neural network, but it's not a normal neural network. Normally, when you have a neural network, it has a fixed architecture. It has a certain number of layers. You initialize it in the beginning, and then you just tune the weights. This is a neural network that we call dynamic neural network. It starts with nothing. It has only input and an output or multiple outputs. Now, as it hears different sounds or it sees different data, it's going to make neurons, it's going to make features that are receptive to the data that it's seeing. So this thing that you see, this is the internals of the agent. And what you see here is the number of imprinted features. This is a number that's moving. Now, if I become quiet, you'll see this number is going down. If I say something, this number is going to go up. What's happening is that as I say, as it agent hears new audio, it generates new features that is specific to that audio. And if I become quiet, then it deletes the features that are not useful. And by doing so, the neural network architecture can evolve as it learns. The second part of the network is feature tuning using gradients. This is close to what we already do in our neural network. We do some sort of gradient descent, but these are recurrent features. And because we are learning online, gradient backpropagation is no longer a good algorithm for computing gradients. So you're using a different algorithm, which is inspired by RTRL. If you're interested, there's a reference at the bottom, which can estimate these gradients much more efficiently and do it online so they can learn without any delays. The third important part of the agent is linear prediction using nonlinear features. So now that you have these features, you're going to learn something. Normally, you can think of it as the last layer of your neural network. And normally when you train neural network, this layer is nothing special. You just have a normal gradient descent on this layer and everything works out fine. But turns out if you want to learn very quickly, which is our goal here, the methods that exist out there are not good enough. And so we had to come up with a new method just for the last layer of this neural network, which is key to making this work. And the final part is continual pruning. So we're going to delete features, delete neurons that are not useful, and we're going to do it continually. Okay, so this was prediction, and prediction is not that interesting. Really, the more interesting part is control. Can we use this algorithm for decision making? So now I'm going to show you a demo of using this algorithm to do some control. And again, the goal is to do it in real time, so you should be able to see it learning. So let's have a simple agent. Let's say we have an agent that has 3 actions. Is there a question? Yes. Salman, what's the question? I think there is a raised hand. You can just unmute and ask the question. Oh, it disappeared.
Hey, sorry, it was a mistake.
Oh, okay, I see. No problem. Okay, so the agent has actions, and let's say in this case, the agent is going to have 3 actions, and the agent will be a simple avatar moving on the screen. You'll see it soon. The action 0 just means go straight. Action 1 means turn right. Action 2 means turns left. And then if there are ties, if the is yes, so Wes.
There's a question in the chat. I was just trying to bring your attention to it.
Okay, what are we predicting? Value function. So in this case, it's a very good question. We are predicting the reward, and the reward is given by this thing that I have in my hand, right? This thing that I showed you earlier. If I press one button, the agent receives the reward of +1. If I press the other button, the agent receives the reward of -1. So in the previous demo, I was pressing a note and giving the agent a reward, and it was trying to predict that reward before it happens. Okay. So let's try to do some control. In this case, if the value, so we're going to learn a value function. The value function is going to have value function for each action, and the agent is going to take greedy action with respect to its value function. We're going to initialize all values to 0, and then we're going to see if we can teach it in something interesting. Okay. Can't move this. Okay, doesn't matter. So I'm going to reset the agent. I'm going to give it 3 actions. And that's the agent. The small puppy you see moving on the screen, that's the agent in this case. So what I'm going to do right now is taking action 0, which means it's going straight. And the reason it's doing that is because the value of all actions is 0. And remember, if there are ties, then the agent picks the smallest action. So what I'm going to do now is I'm going to play a sound, and I'm going to give the agent negative reward with this clicker. And what agent should learn is that, well, it should learn that the last time it heard the sound, it got a negative reward for going straight. So the next time I play the sound, it should do something else. Maybe it should turn left or right. So let's try that. Okay. So you can already see that if just from one sample, you sort of learn that if I play that sound, it should turn left. And we can also teach it to turn in the other direction. Let's play a different note and then give the agent negative reward until it goes in the other direction. Okay, now I have 2 notes, and I can change the direction of the agent by playing those 2 notes. So one direction, other direction. So that's really doing control with the real-time learning system. You can see learning happening as in front of your eyes. Now, let's go into more details of how this system is working. What are the subcomponents of the system? So we have the observation, that's the audio data coming in, that's the Fourier features that I told you about. And then it's making these features that I told you. It's generating new features all the time based on these observations. And then it's using those features for predictions. Once it finds features that are useful, and when I say useful, I mean features that are being used in predictions that have large outgoing weights, those features become tenured. And then they stay in the neural network forever. It's not forever, but they're not removed immediately. If a feature is not useful, it will be removed immediately, and that's why you would see that number going down when I wasn't speaking. So let's look at how these features are generated, and then we'll look at how these features are used for making predictions. So we generate features by a process called imprinting, and the idea behind imprinting is that you want to make a feature that is tuned or specialized to what the agent is experiencing. So let's take an example. Let's say that the time dimension goes from top to bottom, and you have an observation. You have 4 observations in this case, and you have some features that's just the internal neural network at given time, t-1, and you want to make a new feature at this time step. Let's say the solid means feature is 1, and the lines mean the feature is 0. Now, if you want to make a feature at time t, that gets activated when the agent is in the same or similar state, then you can make a new feature and you can connect it to existing features with positive weight if these features are active. So F3, X4, we are connecting this feature F4 with weight of +1, and this X3, we are connecting this feature with a weight of -1. Let's say it's a RLAI feature. Now at time step t+1, if this is your configuration, this feature X4 is not active anymore. F3 is not active anymore. So that means that F4, the value of F4 is going to be -1, and X3 is active. -1 means if once you apply ReLU, it is not going to have any value. It'll be 0. Next time step, again, X3 is active, X4 is active. This cancels out, and if the feature if the match is not very good, the feature is not going to be active. If you see something similar again, so in this case, the value of X4 is the same, the value of F3 is the same, the value of X3 is the same, then this feature will be active. So that's how features are generated by imprinting. Now, the second part is how do we make these features? How do we use these features for predictions? And I think that is the more important part. For this, we had to find a lot of fixes. We had to fix normal TD learning algorithms in fairly big ways to make this work. The problem was that when we took existing algorithms, for example, TD or true TD lambda or true online TD lambda, they worked fine when the step size was small, but as soon as the step size was very large, they would become unstable and they would diverge. And so the goal was to fix that, and that's what we did and proposed a new algorithm called SwiftTD. The key ideas in SwiftTD are that it builds on true online TD lambda, so it takes an existing algorithm, probably the best algorithm for TD learning, and then it adds two new ideas to it. One, it adds step size adaptation. So instead of having to set the step size yourself, the learner can learn the step size using data. And the third is that it has a bound which makes sure that you're never diverged. Your step size is never too large. So let me show you that as well. This is a separate demo that I can show you. It's on my website, so I'm going to open that. I don't know if you can. Okay. So what you see here is the agent learning using SwiftTD on Atari, and it's gonna try to predict the discounted value of the reward. This is a plot where you see the reward. The reward is the same as the reward used in the game of Atari. In this case, the small chicken, whenever it crosses the road, it'll get a reward of +1. Now, the idea behind SwiftTD is that your step size can be bad, but it'll still recover and learn well from it. So we're going to start with a very small step size. This is 10 to the power -7. If you took your normal neural network and you started with a step size of 10 to the power -7, you would not learn anything useful. But what SwiftTD does is it increases the step size because the step size is too small. And this is a plot where you can see that it's increasing the step size over time. So if we wait for, let's say, 40 seconds, you will see that it'll be able to make fairly good predictions by increasing the step size over time. So we are trying to predict the discounted value of the blue value, and the red line is the prediction. Let's wait for 20 seconds. Okay, so you can see that it's predicting something now, even though it started with a very small step size. You can also see that this learning rate is very high now, even though it was very small in the beginning. Now let's do the opposite. Let's start with a very, very large learning rate. Let's say it's 10 to the power 0, which just means it's 1. Now, if you took a neural network and you started with a learning rate of 0, it'll just diverge. So let's see what happens. I'm going to reset the learner. You can see the learning rate is very large, but it's going down immediately. So instead of diverging, it's still adjusting the learning rate to make it smaller and smaller until it's going to find the right one, and it's going to be able to make predictions with that. And the predictions are no longer as good, but if you just wait enough, it will learn to make the right predictions over time. So this kind of robust learning where the agent never breaks, doesn't matter what learning rate or step size you give it, was crucial to make online real-time learning work. Okay, now I'll go back to the slides. And this is where I was. Okay. Now, what I showed you was live demo of SwiftTD, but I can also show you how SwiftTD works in. Actually, let me fix one thing. Window. Okay. If you can't see the slides move, let me know. We can also see how SwiftTD works in experiments. So we did a lot of experiments on the Atari environment for prediction, and I'm going to compare the performance of SwiftTD to true online TD lambda, which is, like I said, probably the best algorithm for online learning, online TD learning. On the x-axis, you see all the Atari games. Now I have normalized the error of true online TD lambda to be 1. So we're going to see how SwiftTD performs relative to true online TD lambda. and lower is better because this is prediction error. And you can see that it performs better than true online T lambda in every single environment. And this is across hyperparameter settings. Now you can also visualize what the prediction look like. So this is one game, it's Atlantis, and the gray line is the prediction that the ideal prediction, the ground truth prediction that the agent is trying to learn. And if you run true online TD lambda on this game, it learns something like this. Okay, so can't see I don't see a graph. I see. So it doesn't let me go to the slideshow. If I go, then you can't see it, which is not great. Okay, let's try. Okay, so I guess if I don't go in slideshow, I won't have my animations, but that's okay. I can just present without that. So this is the graph that I was showing you before, the performance of true online T lambda versus Swift TD on all Atari games. Lower is better in this case. And actually, maybe let me connect a second monitor, and that might fix the problem. Okay, that works. Oh, that's not what I want. Okay. Yeah. And then this is the predictions learned by Swift TD versus true online TD lambda on all different environments. You can see that it learns significantly better predictions than true online TD lambda on a lot of the games. You can also visualize the step size it learns. So Swift TD is learning a different step size for different parameters, for different input features. And if you look at different games, so if you look at Pong, for example, you can see that the step size is large for trajectories that the ball takes, and it's smaller for everywhere else. On Space Invaders, you can sort of see the step size is large for the trajectories that bullets takes, and that's because bullets are predictive of the reward, whereas it's much smaller everywhere else. Okay, so these are two examples of real-time learning, but why do we care about that? Why do we want to learn in real time? Why is it not sufficient to just learn once, let's say on a large neural network, and deploy it and then use it forever? Well, there are cases where it's not possible to learn everything in advance. There are cases when your data stream is different in deployment versus whatever you do before deployment. And in those cases, if you can adapt in real time, you can perform much better using significantly less computation. So let me give you a concrete example of that. A concrete example is, this is a competition that me and my friend Abhishek and colleague Abhishek participated in. Abhishek is also a PhD student here. And the goal of the competition was to take EMG data from this headset, the headband that you can put on your head, and do decision making with that headset. Now, the problem we noticed was that if I put this headset on and do something, the data looks very different than if Abhishek puts this on and does something. And that's because our brains are different. And this is true for every person. If you put this headset on and did something like moving an eyebrow, the data would look very different. That means that it's not possible to train a network beforehand and just ship the model. And in fact, this is one of the biggest problems people face when they're trying to build brain-computer interfaces. It's also a problem that I'm probably sure that the Neuralink team, when they're trying to use data from the brain and take action, that they face. And their solution is usually a 30-second calibration when to the user, but it's much better if you could just do continual real-time learning forever for as long as the agent is using using the system. So we thought about that. We said, okay, let's use the algorithm that I just showed you on this data stream and see if we can do something interesting. So we took the algorithm, and without any modifications, without any modification or hyperparameter tuning, we tried to control the same puppy, but this time data coming from this headset. And this is the video of that. This is Abhishek who trained this, and this is after about 5 minutes of learning. Let me play that. And what you should see is that in 5 minutes, Abhishek was able to train this dog to turn left or right by using different eyebrows. So if you lift this eyebrow, it turns clockwise. And if you lift the other eyebrow, it turns anti-clockwise. Now, if you were to take data beforehand and train it on it, even hours of data cannot give you performance that is this good that you can achieve within 5 minutes if you just learn on the actual data. So I have a second demo as well. This is to demonstrate how efficient these algorithms are. So normally when you have a neural network that is very dense, you have to do a lot of computation at every single layer all the time. The way these dynamic networks work is you only do computation for neurons that are active. You don't do a computation anywhere else. And that means that you can be significantly more computationally efficient. So we deployed this algorithm on an Apple Watch to make predictions on Atari. And after about 5 minutes of learning, it can make fairly accurate predictions while learning on the watch. So here, if I'm going to scroll, and you're going to see that the blue is the prediction and the green is the reward. And the predictions are fairly accurate. Everything is learned here on the watch. Okay. So that's pretty much it. The conclusions that I want you to take away from this is that if you want to do real-time learning, then it requires rethinking a lot of the core algorithms that we believe in. Even what we do in the last layer of the neural network, even that is not sufficient. And in our case, we had to come up with a different algorithm with a lot of changes to make it work. And real-time learning is not just about scaling to larger networks with more data set. There are algorithmic problems that need to be solved if you want to make it work. And and if you want these systems to work well in the real world, in a lot of applications, real-time learning is almost essential because you cannot predict a priori how your agent would be used in deployment. And so with that, thank you for inviting me, and specifically thank you for Ahmed for scheduling everything. And if you have any questions, I would love to answer them. Yes.
You can unmute and ask the question if you have any question.
What was the frameworks that were used for the real-time examples that you gave?
Framework as in?
I mean, it was NumPy, PyTorch, or...
I see. No, so the interesting thing is, as soon as you want to do something that is very different from existing neural network, which is what I'm doing here. Existing frameworks don't work well at all. So all the code, everything was written in C++ by us from scratch. And if you try to do it in Python with those libraries, you can't, or it is much more difficult to do it that way. So there are basically no frameworks.
Oh, nice. So you must have used the camera libraries and that stuff for the embedded, or like in Apple Watch deployment. You must have used the Metal or something like that. So you must have used the native frameworks there.
Yes. So right now it's not GPU accelerated. You could do that. Okay. Right now it's a single threaded C++ code that is doing all the thing. Metal would be the way to go if you want to make a product out of it. Metal would be much more efficient. You're right, but we're not doing that right now.
Okay, nice. Thanks.
Yeah.
Can you tell me how is it different from the current reinforcement learning algorithms? Like, I missed few minutes at the start.
Right. So the biggest difference is that the current reinforcement learning algorithms don't try to learn in real time. There's a delay between the feedback and learning. So the examples I gave in the beginning were, let's take DQN, right? You have a buffer of 1 million, you're going to sample, let's say your agent does something, gets negative reward. You're not going to learn from that immediately. You're going to throw that data point in the buffer, that you're going to sample a mini batch from that buffer. And the impact of that feedback on the behavior would be delayed by many, many, many time steps. Also, your step size is very small. So it's even more delayed. If you take PPO, for example, what you do is you collect a batch of on-policy data. So again, all the feedback you're getting while you're collecting that batch of data, you're not using it. You're just collecting your batch of data. Then you have constraints on your policy so it doesn't change too quickly. That the result of that is, again, that you cannot learn something very quickly. Now, if you look at animals or humans, they're very capable of learning very quickly. If you touch something and you get shocked by it or it's very hot, you would immediately learn to not do it again. So that's the behavior that we are looking for in our agents when in my PhD, and that's something that existing algorithms cannot do at all.
But in classical, methods like tabular methods, you don't have a replay buffer, right? You just estimate the value of each and every state,
Yes.
right?
So
So how is that different? I mean,
yes, it's you can think of this as making similar algorithm as the tabular one, but making them in the function approximation case. So this is not tabular, this is function approximation.
yes, yes. Okay.
You're right that in tabular setting, we already have algorithms that can do this, but tabular setting is not very useful for applications. So our goal is, can we develop similar algorithms in the function approximation setting?
So your states are continuous in this setting. Your actions might be discrete, as you showed.
Yes, so
Yeah.
yeah, the state is continuous. It's just audio data in this case. The actions, right now we're using discrete actions. We are working on
Right.
extending this to after critic so we can make the actions arbitrary, but that is not something that I showed today.
Right. Thank you.
Yeah, thanks. Kushan.
Yeah.
Yeah.
Hi, Khurram. Thanks for the wonderful talk. So, I had a question regarding. So, you mentioned that this continual learning thing, like, so, uh, there has been previous work like from DeepMind, GenXFang, and stuff. Like they look on continual learning in terms of preserving some of this old structural knowledge and then building on top of that this fast learning things. But I also skipped like a part of your talk, but like I was wondering, like, is your like Swift ED, for example, like does it rely on this like big underlying structure and then on top of that do this fast learning, or is it like just forgetting everything that it learned before and then starting from scratch?
Right. So it doesn't rely on a lot of prior learning. Like I don't know which the paper you talked about, but I know that DeepMind has this paper, something called ADA, where they do a lot of meta learning in the first, and then they show that once you have done billions of years of meta learning, you can adapt quickly. So this is not doing that. It's learning from scratch, but it doesn't mean that it forgets everything. So for instance, in the beginning, I don't know if you saw that, I was showing like learning some audio notes and doing something with it. If you come back to that, if you teach that agent 50 other things and you test it on the first thing, as long as the new thing it learns were not, the stimuli was not the same, it would remember the old thing. And in fact, it would remember the old thing indefinitely. So in a way, these dynamic networks don't forget catastrophically because they're very sparsely activated, and a lot of the knowledge is just preserved, because if your network is not active, that part of the network is not going to be updated with your updates.
So how much of that like learning that it doesn't forget the initial features like is like just memorizing, or is it just like generalizing? Because if you learn 10 different things, you learn them either to compartmentalize them separately, or would you like try to integrate them into a consolidated whole that's more generalized?
Right. So really good question. I would say the agent is always trying to find the most general feature, but if you teach it, let's say, a few things in the beginning, it's going to learn them individually. But then if those things keep happening multiple times, over time, it will discover more general features. And yeah, so it's a bit of both. It can generalize, it does generalize. It doesn't generalize arbitrarily, which is what I would say neural networks do. When you initialize them randomly, they generalize in arbitrary ways, and then you fix that by gradient descent. Yeah, it's one way of thinking of it is a much more controlled generalization.
I see. Thank you. So does it have any way of like pruning the past knowledge that it has learned?
Yes, it does. So there is one component that I didn't talk about is it incrementally estimates how important a feature or a neuron is for prediction or decision making. And if something is not useful at all, it is pruned. So yeah, it's continually making new things, but it's also continually pruning things that are no longer useful. But if something is useful, that will not be pruned.
So the learned concept or like whatever behavior has to be continued to be relevant in order to survive the process of pruning in a way.
It would have to. So let's say that there's an action agent takes, but it only takes that once a week, right? There's a feature that gets activated once a week. And it's important for when you're in that part of your data stream. Other than that, it's not useful. That knowledge will still stay. Why? Because whenever that feature is active, it is useful. So the agent will keep it. But yes, if there is a feature that it's active all the time and the outgoing weight is 0 and it's not contributing anything useful to prediction or decision making, then it'll be pruned. So it doesn't have to continually prove itself, but it has to contribute something to a prediction sometimes.
I see. And do you use do you hope to apply these to like deep learning, deep RL framework, or like is it yeah, or have you already done that? Like maybe I missed that too.
So I would apply. I'm testing it on Atari. I'm not planning to test it on anything bigger than that, but I am planning to test it on in a slightly different setting. So one experiment that we're doing is that like I have this Apple Watch. It can generate a lot of data. It has a gyroscope and an accelerometer, and we are running this on the watch to predict the values of those sensors. And the idea is to learn a predictive representation on this device. And then once you have that trained, then you can use this for decision making. So you can use it for gesture recognition or controlling a cursor on your screen by just moving your hand without a mouse. So we are testing it on those settings. I would say that's still deep RL because it is using a deep neural network to make those predictions. But we are not. The goal is not to test it on existing benchmarks.
I see. So I've shared like the paper that I referred to by Janex Wang and Seb Kurt-Nelson. So yeah, what it did, like I think it was like quite like publicized a lot. But yeah, they had a task in which shared the same structure, but the rules were changing. So the agent had to like online sort of adjust to the changing contingencies. But yeah, the dynamics of the action mapping onto like changing the perception of the agent, like that remained the same.
I see. That looks like an interesting paper. I will go through it. Yeah, thanks for sharing that. And I see that there are some people from neuroscience on it, so I think I will like it.
Yeah, so I'm from neuroscience, so like the stuff that you talked about, like this continual learning is something that yeah, I'm deeply interested in too. And yeah, I'm like trying to see like the how can I map it to stuff that I do or hope to do.
I see. That makes sense. Yeah, if you want to talk more about the neuroscience side, I think I'm interested in that too. I would be happy to talk maybe some other time in more detail.
Awesome. I'll reach out to you then.
Yeah, for sure.
Thanks so much.
Uh, yeah. So, can we like get to see the algorithm, like how things work? Like you showed the demo, right?
Yes.
I just wanna know how the algorithm works.
So you want me to describe it, or?
No, I mean, do you have a paper? Like, if you have a paper, I'll just go through it.
I see. So there is a paper on SwiftTD, but that part doesn't generate algorithms. That does generate features. That paper is on my website. The paper on generating features, that's something that we are writing. We're going to submit it maybe in a month, and it'll probably be out in 3-4 months. Yeah.
I mean, generating features as in like you're generating features of the state.
It's you can think of generating your neurons of your neural network, the internal neurons, like the first layer, second layer. Like in the beginning, the neural network doesn't have anything. It only has inputs and outputs. But then it uses the data, and then it generates features that it thinks would be useful. Then it tests.
Yeah. My question is like, is it a policy parameterized neural network, like where you have a input, you give input as a state, right?
You get input
Like
as
in the context of RL.
yeah. The observation is the input. Yes.
Yes. So is it policy parameterized in the context of policy parameterization? Are you talking about? I mean, like using neural networks, like you use neural networks as a what do you call as an initialization as a parameter, like for your policy network. The
So
policy network is a neural network basically. Yeah.
so right now, I think policy. I'm not sure what you mean by policy network, but this is a value-based method. Like I'm learning a value for every action.
Okay, you're not okay. Yeah, makes sense.
Yeah, I'm not using actor-critic yet, at least. That's something that we're working on, but this part was not using actor-critic. It was just like Q learning.
DQN probably I could relate to DQN.
Yes, I think that would be. Think of DQN, but no buffer, no target networks, just learning one sample at a time, and then
Right.
all the problem is how do you make it work, and this work is to make that work. And I don't know if you have read about TD Gammon. That was like a 1992, 93. That would be the closest thing in public that you can read about it, because TD Gammon also learned one sample at a time. It used a neural network, and it didn't use buffers or replay.
So are you planning to use a mixture of both? Like
Probably not, because there are a lot of benefits you get if you throw away buffers. So you can use eligibility traces. You can save a lot of computation. So the way I like to think about it is that, of course, we want large agents. We don't want to have small agents. We want to have large, gigantic agents. But instead of having, let's say with DQN, you can have an agent with 100 million parameters. You can train that on one GPU. If you use these algorithms that don't have buffers, you can probably have a billion parameter model on the same GPU. So it's a way of using compute in a different way. Instead of using it on buffers or resampling or mini batches, we want to use all the compute to make the agent as big as possible. And then we're going to use these online algorithms for learning.
okay, thank you.
Yeah, thanks.
Do you also use an offline version here?
Do I use offline version? So this is all online. There is no offline. The data is never stored. The agent uses it, learns it, throws it away.
Okay, thanks.
Like, can we like probably if you have an offline data set, like you have one sample, like you can sample one sample at a time and then probably do it similarly, right? Does that work?
I would say that in the prediction setting, if it's on policy data, then yes, you could do that. In fact, there are some benchmarks that I'm testing it on, which are similar, which are like these, that people have collected data, but it's on policy and for prediction. But as soon as we go to control, then it doesn't work, because you want the agent to be able to take any actions, right? And then the data set will not capture that.
I mean, even though if it's off policy, like you're collecting a data set, and then I mean, like basically, yeah. I don't know, one sample at a time of policy.
Yeah, you
Would
could
that
do.
work?
You could. Like but I would say that if you are going to use, if you're going to learn from a data set, then you probably don't have to do a lot of the things that I'm doing, right? Because, for example, let's look at SwiftTD. Like a lot of the components of SwiftTD are about how do you make eligibility traces work with online learning? How do you make it work well? If you have an offline data set, you don't need eligibility traces. You can just compute your multi-step return beforehand. It's very cheap, and you can just use the right return, right? So I would say you could use it, but should you use it? The answer is not as clear. Maybe it's better to just use existing algorithms if you're in the offline setting.
Okay. Thank you.
Yeah, thanks.
So I had like a question regarding the like how do you store these sort of learned behaviors like into these what you call tenured something forgot.
Tenured features. Yeah. So
Yes, sir.
Everything is stored in the neurons of the network, like a neural network. It's what happens is, your input, you get some input, the observation, that those input features are connected to some other features. So they will activate those features, then those features will activate some other features, and they're all connected to the prediction. And so then they'll make a prediction. So all the knowledge is stored inside the neural network. And then
So when we are
yeah, sorry, go on.
so you're actually recalibrating the weights like in an online fashion.
Yes. So the paper that I was linked, like there's a paper we published last year about how do you tune the weights of recurrent networks using gradients, but more efficiently, so not back propagation. So we are still using gradient descent, just like normal neural networks, but we are not using back propagation to compute the gradients. We're using a different algorithms that is more efficient for online learning.
I see, that's quite cool. So the paper that I shared, like in that, like they don't actually retune the weights. What they utilize for the meta learning or the relearning is just the dynamics of the network. So the weights are like sort of static, like through like cross task learning and stuff, and then they retune according to the rules of the task. So how like how would can that approach sort of complement your approach like in a way and be implemented together as
I think that because these are also neural networks and like recurrent networks, and there is some meta learning going on that I didn't talk about. They can learn something similar in the hidden state, but they sort of have both properties. But I don't see a value of this two-step process where you first train one network and then you fix the weights and you just change the dynamics. You could do it, but I think it's much cleaner if it's just learning online in real time. Give me 1 second. I'm just going to be back in 1 second. Wow, sorry about that. Yeah. So it's like that. Now I actually remember this paper as well. I think what they show, and a bunch of other papers showed the same thing at the same time, is that the recurrent network dynamics can capture learning. They can capture learning algorithm inside them. That is true. But I think our goal is to not just rely on meta learning, but also figure out what the right algorithms are. And then maybe the rest of the things the agent can meta learn.
I see. So like on your previous like comment regarding like the utility of like these two approaches working simultaneously. So as a neuroscience person, like the like yeah, it's the weight recalibrating like the approach that you use is something more in terms of the long-term memory thing that we like the neuroscientific theories like we might be doing more in sleep, while the more of the dynamic stuff is more of the daytime stuff that you actually do that like in the real world and then in sleep. So have these two states like of both working and complementing each other uh, at different time scales and different sort of modes of a passive mode, of an active mode. And I don't know, like I feel like that kind of approach might be necessary for the general AI stuff.
Yeah, I think now I finally get you. In fact, it reminds me of a paper I read. It's called Complementary Learning System in Brain,
Yeah,
1996. Maybe that's what you
Bruce
were.
McNaught, yeah, and
Yeah.
James McLaren, yeah.
I think of that dream part as planning. Like, when your agent is not experiencing anything, it can still plan. Experience replay buffer is also sort of like planning. I agree with you that that is important, in fact, crucial. Um, there are ways to make planning work with this system. What we are imagining is that instead of planning by storing the observation, let's say you want to plan also at an abstract level using the features. My guess is the brain also does something similar because it doesn't store raw sensory data. The dreams that we dream, they're very abstract, probably some planning happening at a higher level. So I agree with you that I think that is crucial. That is not something that we have worked a lot on, but we fully realize that that is essential. Like it's on the agenda, but maybe a few years down the road because the stuff we are doing is already fairly challenging.
Awesome. Yeah, that's understandable. So these networks that you're using, these are feed forward or recurrent? Like what are these?
These are so all the neurons are recurrent.
I see.
Yeah.
Then there is potential for it to like have something in the dynamics and then that being recalibrated just through the dynamics sort of rollouts in a way.
Yes, yes. It can learn that. It is possible that if I just run this at a much bigger scale with much more data and run it for much longer, it will learn things inside the dynamics as well, or it will learn to learn using the dynamics. I think that is very possible because you can like in what I was showing you right now, it wasn't using LSTM cell, but in the paper we wrote last year, we use LSTM cells, and they can capture a learning algorithm, which people have shown. So all that could happen. Yes.
Awesome. So there's this paper on world models by Schmidt-Huber's lab. So he had like that kind of system in which like there would be an predictive RNN that would sort of predict the next state given the action and stuff, and like and the auto encoders, generative variational auto encoder that could detach itself, and then you could have a recurrent system that could learn in a dream-like state in a way. So having that coupled with it seems quite interesting.
Yeah. No, I think that would be very cool. Like having some sort of planning at an abstract level, similar to the word model paper, I think would be very interesting.
Awesome.
Yeah.
Thanks so much.
Yeah, go on.
You can go ahead. I was just thanking.
Oh, yes. I was just curious. Like you were saying that you are not using back propagation for
Mhm.
computing the radius, right? What was it? Like what you guys are using?
So this is a similar to RTRL, real-time recurrent learning. It's like instead of doing, but RTRL is very expensive. So there are ways you can make RTRL not be expensive, and that's what we're doing. Like without introducing any bias, if you restrict your neural network in some ways, you can make RTRL scale linearly without, and that's what we're using.
But TD learning is biased, right?
TD learning is, sorry?
Biased.
TD learning is biased, that's true. But that is, I would say, a useful bias in a way. Like if you think about how animals learn, the bootstrapping that they do is almost crucial to make it work. And if you have limited data, then there are also some theoretical results that show that TD learning can generalize better because it can sort of switch trajectories and make data that doesn't exist. But yeah, it is biased. But if the goal is learning quickly, I think there is no way around it. You have to sort of accept some kind of bias.
Yeah. Okay.
Lastly, if you could shed some light on how the after increasing the step size by a large magnitude or decreasing it by a large magnitude, it did not act like how gradient descent would do, like explode in a certain way or vanish. So yeah, if you could explain how that happened.
Yeah. So if you maybe I should clarify one thing. Like the Swift TD learning fast, most of the fast learning happens in the last layer. Everything before that is still learning very slowly. Now, why does it not diverge? In the last layer, there are ways to estimate very accurately when your step size is. When that happens, the algorithm automatically makes the step size small. So it kind of makes it impossible to. It doesn't do an update with a step size that's too large. It reduces it immediately. If it's too small, if the algorithm sees that, well, my last 20 gradients were pointing in the same direction, that's a sign that the step size is too small. It should be larger. So it increases it over time. So that's what it uses. It increases it over time, or if it's too large, it'll decrease it. And by doing so,
I skimmed the paper and it said that there is a hyperparameter eta which controls this. I did not get it, so that's why I'm asking.
So the hyperparameter, that one controls the maximum learning. So okay, let's think of this way. Let's say your agent predicts 0 and the ground truth was 10. Now you want to do an update, and there's a question of how much of the error do you want to reduce? Do you want to go from 0 to 10 or 0 to 5? Like you want to reduce half of it? Maybe you don't want to reduce all of it because there is stochasticity in the environment. So the eta parameter controls what percentage of the error at max you will reduce. Clearly, going above 10 is not useful. That means your step size is too large. If your eta parameter is 0.5, that means you'll fix the error halfway through. If it's 0.1, you'll fix the error about 10%. If that makes sense.
Okay. Thank you.
Yeah, thanks.
If you don't have any other question, I guess we can conclude the talk here.
Yeah, sounds great.
Thank you so much for your time.
Yeah, thank you for having me. This was fun.
Yeah. Take care, everyone. Bye.